how nice this campus is. I remember my engineering school being dark and dingy. I wish I had a second shot to come here. This is a great campus. It's also wonderful to be here with so many different stakeholders from around this PFAS challenge, government officials, industry representatives, academia, etc. This is a big challenge, as we've heard from both Nick and Katie. It's going to take all of us working together to overcome it and come up with the solutions we need. Nick mentioned that this project is complex, or this problem is complex but not insurmountable. And I think that gives us all an opportunity to work together and make a difference, not just for our generation, but for future generations as well. I also wanted to thank Tom and the Center for Translational Research for bringing us all here together today. It's been a great event so far, and I look forward to the rest of the day. As Nick mentioned, I'm Chris Lowe. I'm the Chief Technology Officer for Veolia North America. Veolia is a global company with a big presence here in New Jersey. We do work across the water, waste, and energy sectors, and specifically in water, we have treatment technologies for municipal water and wastewater treatment, and also industrial applications as well. And a different part of the business, but we own and operate water and wastewater treatment plants through our utility division. And we also operate and maintain both water and wastewater systems on behalf of municipalities across the country too. So PFAS is a topic that both myself and my team have spent a lot of time on over the past several, if not many years. We're looking at different treatment solutions. We're looking at how to deliver those solutions most effectively, to get the most bang for our buck out of the capital investment that's needed, and looking at how we optimize operational costs as well. Our goal is clearly to find ways to meet the upcoming federal guidelines, but also to do it in a responsible way for our customers and our ratepayers as well. And today we're going to focus our discussion on the Stanton Drinking Water Treatment Plant, but this is only really one piece of a much larger PFAS treatment program that we've got here at Veolia. And this program represents a significant capital investment and represents our commitment to provide safe and compliant drinking water to our customers, which number over 2 million across the country, many of whom are right here in New Jersey. So my goal here as we talk about the Stanton project is really to share some real experience that we've had delivering a solution to PFAS in our drinking water systems. All right. I'm obligated to give a little bit of a disclaimer. Sorry about that, but this is really just an acknowledgement that things are changing fast in this space, as everybody knows. What we know about PFAS, what we know about treatment of PFAS, and what we know about regulations is changing very quickly, as we know. So what you're hearing today is valid today, may not be valid tomorrow, who knows. All right, let me introduce to you the Stanton Water Treatment Plant. So this is a plant that's owned and operated by Veolia. It's located in Delaware, just outside of Wilmington, which is right across the river from southern New Jersey. It's, to our knowledge at least, the largest surface water PFAS treatment system in the US today that's operational. That's going to change given the other plants that we know of that are going to need treatment. But for now, we stake that claim. And it supplies drinking water to about 140,000 different customers in Delaware. When you think about this treatment, the PFAS treatment system at this drinking water plant, it represents about a $43 million capital investment to put that treatment system in. So it's not an insignificant investment, of course. A couple of points here. First, I mentioned that this is a surface water drinking water treatment plant. Obviously with surface water, we have to think about high variability in the water intake from a seasonal perspective, both from organics and PFAS contamination thinking about things like runoff or drought or precipitation as well. Surface water plants also tend to have larger flow rates. So you're looking at a treatment system that has to be able to handle larger flow rates at relatively low concentrations of PFAS to treat, even though they are still above the federal and state standards. The second point I'd like to make about this slide is really about the project timeline. So when you look at the slide, you can do the calculation. It took about 2 years, just over 2 years from the time that the design build contract was issued to have this treatment system online, which when you're talking about a system this size is quite an accomplishment. We wouldn't have been able to do that without the contracting model that we went ahead with, the design build model, but also the partners that worked with us throughout the course of the project. I mention that because, Nick, you said earlier, this is a race to find a solution. We do have a little bit of a race against the implementation of the federal guidelines as well, which even though officially are 4 years away from today, we're sitting in April 25, they come into effect in April 29. 4 years is really the blink of an eye when you're talking about the size of some of the treatment systems that we have to put in place. So at Veolia, we like to be involved in PFAS treatment from one end of the project right through to the other, and we call that our end-to-end solution, or beyond PFAS. But in this case, specific to the Stanton drinking water plant, we were involved quite early. This watershed had been tested for many years, and we specifically started testing for PFAS at Stanton back in 2018. We quickly realized that PFOA was the main concern, and we were looking at concentrations in the 15 to 30 PPT range over time, which is well above the 4 PPT MCL limit that the federal government has come out with, federal EPA standards. From a design and engineering perspective, we're always looking for the most cost-effective treatment solutions. But not only that, in this case, we were looking for the right partners to implement that solution. I mentioned that was a big factor in achieving the timeline that we were able to achieve. But this partnership group, we worked with CHA and Ronca from a design build standpoint. CDM helped us out with a lot of their services. You think about it as a bit of an owner's engineer. And then Carollo really helped us on the pilot program, which we'll talk specifically about in a few minutes here. On the operations side, not only is the PFAS treatment system intensive from a capital standpoint, you have to think about operating it over the long term, which is a costly endeavor as well. So we're always looking at how do we operate in a way that optimizes those costs. And certainly from a final treatment standpoint, in this case, at Stanton, we chose a carbon solution, a granular activated carbon solution. So this was a lot about how do we think about reactivating that carbon. At this point, we're sending that carbon back to our supplier to be reactivated and reused in different applications. But we're starting to think about whether or not we could actually reuse that reactivated carbon at Stanton in the treatment plant. We still have a lot of work to do to see if that's feasible and possible, but that's an idea that we have. And of course, with Veolia, if we do need to dispose of that carbon, we have incineration operations within our portfolio that can do that as well. All right, let's talk about the treatment system itself. So at Stanton, like I mentioned, it's a GAC adsorber system. There are 21 trains of 2 vessels each, lead lag configuration, so a total of 42 vessels. The empty bed contact time at design is about 10 minutes per vessel. I know I'm getting into technical terms here. When we operate, the empty bed contact time will be almost twice that, given the average flows. And the cost, again, coming back to cost, the carbon vessels and the media together are about $15 million of that $43 million. So a couple of things, to think about here on the slide. There's the vessels each have 40,000 pounds of carbon in them. So if you're good with your multiplication tables, you can quickly calculate you're over 1.6 tons of carbon in this plant at any given time. So you start to think about, where do I get that much carbon? Can I secure that carbon supply longer term? I'm gonna have to change out that carbon once it's spent. So we put a lot of thought into this. We're already negotiating carbon supply contracts with key suppliers. So we have that not just for Stanton, but for our other treatment systems in our portfolio as well. It's a big question. And by the way, this is a 30 MGD design flow plant. We have another plant in our portfolio that's 180 MGD, so 6 times the size. Gives you a sense of the amount of carbon we might need there. I'm not even talking about all of the other treatment systems that are going to be going online here, not just in New Jersey, but across the country as well. So that carbon supply is going to be a big question for us. The second thing that's important to note here is that the vessels at Stanton were designed to either hold carbon or ion exchange. So it gives us that flexibility first to optimize our operations if we find that one or the other tends to work better over time. And it also gives us a little bit of versatility if different regulations change or we're trying to treat for different micropollutants over time. Microplastics was already mentioned. Who knows what that treatment technology is going to be. Hopefully we've given ourselves a little bit of versatility there by thinking ahead with that. I'll talk a little bit more about cost. I've mentioned the numbers a little bit so far. This is a huge challenge for everybody when you think about the complexities around PFAS treatment. It's a huge challenge for municipalities. It's a huge challenge for us as a private utility, but also will become a huge challenge for customers and taxpayers were mentioned, and ratepayers within our system as well. If you look at the chart on the right-hand side of the page, it shows a little bit about our capital costs. So the kind of flat or slowly increasing trend line is a typical amount that we would invest in the drinking water system in Delaware on an annual basis. And that big green triangle you see in the middle is that capital investment, that one-time spike to get this PFAS treatment system online. So it almost doubles the amount that we have to invest in that system for the period of 2 to 3 years. Even then, that's a relatively short-term impact. When you think about operating costs and you look at the numbers on the left-hand side of the page, you quickly realize that just operating the PFAS treatment system at the plant is twice as expensive as the current operating costs. So you're dealing with 3 times the operating costs as what you're dealing with before, which is a much longer-term impact over time. We're planning to operate this plant for years and years into the future. So first, it makes us think a lot about how do we optimize those costs, not only in the capital stage, but also in the operational stage as well. I'll talk about some ways that we're doing that as well. And then secondly, there's been a lot of kind of guidelines issued or studies issued about how much is expected to be spent on PFAS treatment in different states or in the US over time. What we're seeing and what we saw at this plant is that the actual costs far outstrip those that have been predicted in those reports, I'll say. All right, one thing that, retrospectively was a great decision by the project team at Stanton was to invest time and money, frankly, into having a pilot at the site. The pilot obviously helps us to refine our design and operating conditions. It tells us a lot about what we can and can't do given the water coming into the plant. And that pilot started running about a year ago, back in May 2024. And it's got the ability for us to test different types of carbon, different types of ion exchange resins, and different combinations in a lead-lag configuration as well. It is worth noting that this pilot well it's offered up a lot of benefits to the Stanton plant. Surface water treatment is very local, so we plan on having a different pilot at each of our other surface water plants so we can understand the dynamics of that kind of intake water at each of those sites too. So a couple of things just talking about what we learned through our work being done at the pilot. Certainly, by trying different things, we were able to go from an initial design condition where we expected 6 months of carbon life in each vessel, and we started being able to extend that through different work we were doing with the pilot. Now we think we can get up to 270 days, or about 9 months, and we hope to continue extending that over time as well. Just to give you a little bit of the scale of that impact, each time we change out the carbon in one vessel costs about $70,000. So one train would be $140,000. And if we are able to extend the life of the carbon in each of those vessels just by 30 days, that's a savings of between $200,000 and $300,000 a year on operational costs. So this pilot is awfully important to us, looking at optimizing our overall plant operational costs going forward year over year. Not only did this pilot help us to figure out how we could optimize the life of the carbon in our vessels, it helped us to establish how we're going to start up the plant as well, by helping us to determine how many different bed volumes we need to rinse the carbon out, to get the carbon into spec, and how we could do that in a way that didn't disrupt the plant as well by blending, as we started up the different vessels, in with the total plant flow to keep it in line, and to avoid wasting the water that we would need to get those vessels kind of into spec. All right, so we've come a long way on the Stanton project. This is a project that conceptually started back in 2020, 2021. The design build contract was issued in 2023, as you saw. Now we're in the process of bringing the plant fully online. We started to get the initial vessels online back in March of this year. We expect to have all of our vessels and carbon trains online by the end of May, and we plan on kind of officially opening this plant mid-June, so here in a couple of months. We're really in the process of not only getting that startup complete, but we're starting to sample the full-scale carbon beds, just to make sure we don't have any issues with channeling. We know that the PFAS is being removed as we expected, and we know that we're getting the carbon beds into spec as quickly as possible and as we expect. And of course, from a piloting standpoint, I talked about how valuable that's been so far to developing our operational procedures. We're going to keep doing that, and we keep hoping to extend the carbon life and optimizing our operations. All right. So just to kind of sum it up here and what we've been doing at Stanton, and maybe share some of what we've learned from what's been a very successful project for us, in my opinion. First, we've implemented some procurement strategies. We took the decision to procure the vessels and the carbon ourselves directly from Veolia, which allowed us to control a little bit more the schedule on when we would do that and when they would be delivered, but also helped us reduce the cost. Obviously, the more we do ourselves, the less is subject to markup from the contractors. Not only did we do that, but our procurement process allowed us to get competitively bid media, and we're going to continue to do that. I mentioned the design build team and how that collaboration worked. I really think a lot of the success of the project, not only on timeline, but how we were able to optimize costs, is a result of that collaborative nature, bringing everybody in early on in the project to talk about how we were going to attack the solution. And I would recommend doing it in that collaborative fashion across the board and for any different project. Obviously, when you're adding a treatment system into an existing plant, you need to plan that carefully. So we had we put a lot of work into planning our tie-ins, if you will, so we didn't disrupt the existing plant, and different construction activities so we could keep the existing plant going, of course. And then something we're very proud of is the outcome of the collaboration from that project team was really about kind of reducing and optimizing our capital costs but also our operating costs, as I've talked about. So a little bit of real-world experience to share with you. Just wanted to kind of close on those winning strategies. I think when you're thinking about some of the challenges that I raised, think a lot about obviously cost of not only the capital investment but the operational cost of the system. Think about how common it is to use carbon now in PFAS treatment solutions. When you scale that up across the country, how do we make sure that that carbon supply is there and available to all of us? And then time. I mentioned the timing of the federal, the EPA MCLs that are going to come into effect in 2029. When you think about some of the treatment systems that are yet to be started, how do we get there in time to make a difference? So, and I wanted to give a shout out before I was done. I'm sitting here, I've got the pleasure of being here with Gail Fetcher, who was the project director that delivered this wonderful project for us, and Jonathan Tardif, who leads our PFAS, our overall PFAS treatment program at Veolia. They've both done a fantastic job, not just at this plant, but throughout our portfolio for PFAS treatment. So thank you to you too.